Good. Let's record it. Chapter 3, Kinematics and Dynamics. So what we are doing is, if you see, you have your animation file here, right? So that's our draw vehicle file, and this file, so we are making another block basically. Basically this will be the UAV block. Drawing is just to represent it, but now we are putting some heart and meat to the picture here, and that will be our S function. You've done this exercise, right? This S function will take all the forces. So right now we will not go into details of where the forces are coming from. That will be the next assignment here. One more block added which will compute aerodynamic forces and torques and everything. But in this assignment or this class, we will assume that, okay, somehow there is a force acting in forward direction, there is a force acting in sideways, up and down, and that force can come from propeller. And also next week, whole week, will be spending on how do we compute these forces, because all you have is a propeller, right, in the front, and you have control surfaces, elevator, ailerons, rudder. So the forces will be created using them, but that we will leave for the next chapter. For now, we will just focus on, okay, there are some forces coming, Fx, Fy, all of them are in body frame, and torques, L, M, N. So this block will take 6 inputs, because there are, so you can apply force in forward direction, everything in body frame, forward direction, sideways, up and down forces, and then torques. You have a torque to rotate the vehicle in x-axis, you have a torque to rotate vehicle in y-axis, you have the torque to rotate the vehicle in z-axis. So 6 total inputs to the system, and how these inputs are used to compute all the states, that's the S function. So next assignment, next week, we'll be making a block which just computes forces and moments, and then it will be replaced. So that input will be, so you see, if you don't do this assignment, the next will not be done. So it's all kind of systematic way. And this block will take throttle, delta T, elevator, rudder, and aileron. So 4 inputs will go there, 4 inputs going there, and from 0 to 1, 0 to 1, will compute forces and moments, and that forces and moments will go to your S function here. So, so that's the kind of strategy we have going forward. Okay, let's see. You can see all the 12 states. So you were dealing with 4 states. We will have 12 states in the UAV. 12 states. So the first 3 are the north, east, down position of the vehicle. Second 3 UVW are the ground speed of the vehicle or ground velocity vector, UVW, components of velocity in body frame. So see, now even we have states, but they are represented in different frames, and that doesn't matter. We will be writing equations of motion for them in the next couple of minutes, but first 3 are defined in inertial frame. That's why I've written here, right? First inertial north, inertial east, inertial down. UVW are the velocity, this is the velocity of the vehicle with respect to ground, and that is UVW, okay? And these are conventions. If you see, so the authors of the book have researched, and you will find that when you read other papers available in literature, other books, this is the kind of convention used. So when I say UVW, I will not have to say, that it's kind of given that this is the velocity vector of the vehicle. Okay. Phi theta psi, you already know that's the attitude of the aircraft, which is roll, pitch, yaw, right? And then you have PQR. These are the new terms. PQR is are the angular velocity of the vehicle in body frame. So how fast this vehicle is rotating along X, how fast that is P. So this is P, roll rate, you can call it, or P, pitch rate, Q, and yaw rate, R. Okay, so these are 12 states. First 6 is the First 6 are the linear position and linear velocity, basically, right? In different frames, of course. Second 6, starting from phi, theta, psi, are your attitude or angular displacement, and then last 3 are your angular velocities. So that's kind of makes the state. Now you can think what is coming next, right? We want to find out what is Pn dot, what is Pe dot, what is Pd dot. That's like finding out mathematical model of your UAV, right? So that's what. So these 12 states, I think by the end of this 2 assignments, you should be able to. And I say, hey, what are the 12 states? Maybe that will be a question in the midterm exam, right? Write down all the 12 states of a UAV or something. Okay. So yes.
I'm still a little confused about U, V, and W. So is it just like the inertial framework?
It's body frame.
Body frame.
So how fast the vehicle is moving in its nose's direction, in forward direction. So that's U. And when vehicle is moving this side, it's V. And it does not have any connection because in inertial it will depend what is your attitude. If UVW is known and then you know the attitude, you can tell what is P dot, P dot, P dot, right? And you will use UVW to compute P dot, P dot, P dot. That's how we will get it there. But yes, that's the body frame velocity. UVW is body frame. Forward velocity, sideways velocity, vertical velocity. UVW. Forward, U, sideways V, vertical W. Okay, that's everything with respect to body. Okay, and then PQR are as the angular velocities in body frame. How fast I'm rotating here, rolling. How fast I'm rotating here, Q. How fast I'm rotating along Z-axis, yaw. So these are yaw rate, pitch rate, roll rate kind of things. Okay, they're not exactly like phi dot equals to P or something. We'll have a relationship between them, but they are all in body frame. And it's written there. If you see FB, IB here, and if you see body frames here, you'll see they are in body, inertial, and the phi, theta, psi are all defined in 3 different frames. If you see vehicle frame, vehicle 1 frame, vehicle 2 frame. So phi is defined in vehicle 2 frame, theta is defined in vehicle 1 frame, and psi is defined with respect to the north, yeah, means vehicle frame, right? So intermediate frames. And yeah, picture, if you see the picture is there, right? So P is this, Q along this axis, and R along this axis. Okay, and of course forward velocity is also given U, V, and vertical velocity W. Okay, so these are the 12 states that your S function will solve for. So we will have to set up a first order differential equation for all these equations, right? We need to find P n dot, P dot, PD dot, U dot, V dot, W dot, phi dot, theta dot, psi dot, P dot, Q dot, R dot. So all these. So some will be linear velocities, some will be linear accelerations, some will be angular velocities, some will be angular accelerations. Okay? Okay, let's start with the translation kinematics, right? So our first objective is to find, so now, as I said, we are trying to get the equations of motion, right? That's our purpose. We are trying to get x dot equals to f of xu, right? This is what goes in the S function. So let's start with first 3. What is first 3? Pn dot, Pe dot, Pd dot. What is that? This is the velocity in inertial frame. So now you see UVW are the states of the system, right? So you already know the body frame velocity, and we have to convert it to the inertial frame. That's all we have to do, right? So what's that operation? So that operation will be, because these states are already known to us, UVW, we are already solving for it. So you already know the body frame velocity. All we have to do is convert it, right? You know body frame velocity, that's a vector now. And we have to take this vector, or how is that vector seen in the inertial frame? How do you do it? Rotate it from body to vehicle frame. How do you rotate it? Using this awesome rotation matrix, right? which is, how do you compute rotation matrix? Because that's dependent on the attitude of the aircraft, phi, theta, psi. So the vehicle has 3 rotations before it goes from body to inertial frame, right? So if you know, so phi and theta and psi are also states, so you can compute this, and you already know these 3, so you just multiply by this and you get p n dot p dot p d dot here, which is this matrix multiplied by UVW. Okay? Simple. So when you're putting this is how. So I think the best practice will be you write a function which is rotation matrix. So whenever you use phi theta psi, it gives you a rotation matrix. So write a function in MATLAB. So because this will be used in drawing, this is used in equations of motion, and it will be used in computing forces also. So whatever rotation matrices are being used, I would say write a function for them. Function rotate from vehicle to body. Function rotate from stability wind frame to body. Write them so that whenever needed you can call these rotation matrices for your drawing or for your equations of motion, right? So that will be a because once you get it correct, you don't want to write it again, because it looks simple here, but writing this is a painful thing. You can miss some signs here and there. So C theta means cos theta, and S means sine. So pretty okay. So this is a combination of 3 rotations. It may happen that if I only rotate by psi, phi and theta are 0, so the rotation matrix becomes really simple, 1 rotation. This thing will become 0, 0, 1. So this will be 1, this will be 0, 0. And so it will simplify, but use this matrix. Okay, so that was easy. We have UVW and you get P n dot, P dot, PD dot. Okay. Next is a little complicated. So we are trying to get phi dot, theta dot, psi dot, okay? And because all of these angles are defined in different frames, they will undergo different rotations, okay? Because your psi, if you remember, your heading is defined in with respect to vehicle frame, right? How was your heading measured? The UAV moves and the angle is measured from the north axis. North, the inertial vehicle frame has a north, right? So if I have a UAV, it turns by heading psi. So how is this psi measured? Psi is measured with respect to the vehicle frame's the front axis or north axis, right? So it is defined, this quantity is defined in the north axis. So if psi dot is there, if you, let's say somehow you know psi dot, and I have to translate it to body frame, it will undergo 2 rotations of it's defined in vehicle 1 frame. If you see, we went to vehicle 1 frame. So 2 rotations of theta and psi will take it to body frame. So everything we are doing right now is computing things in body frame, because see, at this side we already have PQR, which are angular velocities of the UAV in the body frame, right? So we are trying to compute, say, if you know psi dot, theta dot and phi dot, what is their relationship with PQR in body frame, right? So that is what we are saying. So psi dot, if I know psi dot, if I can take these 2 rotations and convert it to body frame. So when we are editing, it has to be in the same frame. And then theta dot is in vehicle 2 frame. You can go from vehicle 2 frame to body frame by 1 rotation. This rotation here. And psi dot is like you're always when you're rolling, it is always in body frame. So it does not need rotation. So basically, P definitely is equal to so this quantity does not need any rotation, and when you add these things, you come up with this matrix. Again, you can verify that even though this came through a different way, it is still a rotation matrix and it will satisfy all those awesome properties. So now we have psi dot, theta dot, or phi dot, theta dot, psi dot equals to PQR, but we are solving for this, right? And so just take a transpose of this, and we can write this equation here. Right? No need of inversion, just transpose is sufficient. So when you do that, no. I think there's a confusion here. So yeah, I will take my words back. I think that this is not a rotation matrix in that sense, because if you see, this is not a transpose. You actually have to invert that matrix. Okay, that's why you get this tan theta, sec theta. Okay, so yeah, in this matrix is not the rotation matrix, but when you take the inverse of this matrix, you can compute phi dot theta dot psi dot. And see, it's all like solving equations of motion, right? So now PQR are the states, right? PQR are your states available to you. So when you multiply PQR with this matrix, you get phi dot theta dot psi dot. And we need them, right? Because phi, theta, psi are our states. So now we have equations for linear velocity, P n dot P dot in the inertial frame, and we have equations for phi dot theta dot psi dot. So 6 taken care of, no problem. Okay, so this is all you have to compute. Like when you write the S function, you have to write P n dot equation P dot PD dot phi dot theta dot psi dot. Questions on this? Yes.
Why is it phi dot equal to P?
Oh, it is not equal to P, right? Because it is not equal to P.
Isn't phi dot the rate
So-
of change with the
So you will see that phi dot, so that you will see when you are doing the simulation that when there is a yaw rate also, it will impact your phi dot. So there will be when you start rolling, your vehicle will do also like this because of the coupling here. Yeah, phi dot is not P. Later on, when we are designing controllers, we can assume phi dot equals to P. Simplifications for designing controllers. But for actual simulation, phi dot is a function of phi dot equals to P when there is no other rotations. If you are not rotating, if Q is 0, R is 0, then phi dot equals to P. So okay, so now you see we can just summarize. We got these 6 states equations. One is P n dot, P dot, PD dot by this. So you can use this chart for implementing in. So how I will implement is, okay, P n dot, P dot equals to a rotation matrix going from body to vehicle, which is already a function being called. Just write phi theta psi, which is a function of phi theta psi, multiplied by u v w. And remember, u is what? I don't know, x4, x5, x6. So everything is like a vector. Similarly, this is 10, 11, 12. And okay, so just instead of writing each individual equation, I would say use matrix operations. It will make your life easy, like one line statements. In one line, I can compute 3. In another line, I can compute the next 3. Otherwise, you will have to write all the 6 equations and it will be painful. Chances of getting things wrong will be really high. So use that. Okay, now we move. So remaining, if you see what are our next states, we need to find u dot, because u, v, w are our states, right? U dot, v dot, and w dot. What is u dot, v dot, w dot? Actually, if you think. These are accelerations in body frame, right? So we use Newton's second law for this. So let's say the rate of change of velocity is equals to forces, and F is the sum of all the external forces for now. So this is, we are assuming that, let's say there are some forces acting in all the 3 directions in body frame. So these are external forces. Next chapter we will compute how these external forces come because of aerodynamics, propulsion. M is the mass. So I don't know if you remember last class we ended in differentiating a vector in a rotating frame. So there was a vector P rotating, so your body frame was rotating with PQR. So looked from the inertial frame, it was comprised of two parts. So that's what we are doing. We are differentiating a vector. Vg is a vector, right? What is Vg? It's a ground velocity in body frame, which is UVW, nothing else. UVW. So we are differentiating it in a rotating frame because it is rotating. The body frame is rotating with P, Q, and R. So you see it has two components, linear acceleration component and acceleration because of the rotation. Just from the previous class, that's how that differentiation works out. And which gives us this equation here, right? Means we can make it equal to this, and which is equal to force, because this is acceleration, right? So we need to compute the force of mass into acceleration is force. And so we can all write this in body frame now because these are the forces we can. So FB is all these forces in body frame, and it has three components of those forces, Fx, Fy, Fz. So for now we are just saying that somehow magically you will be inputting. So when you test your simulation, you will say let's increase Fx from -1 to +1 in the slider. So that means the vehicle should accelerate in the forward direction or decelerate in the backward direction. Right? So if you increase y, f of y, the vehicle should go sideways. If you increase fz, it will move up and down based on that. Okay. So in this, your ground velocity is, body frame is UVW. These are all states of our equation, right? We know them. We are computing them in the S function. Your angular velocity, PQR. So basically the dynamics equation comes like this. Very simple equation, like nothing. This can be represented by a cross product. I think it Vg cross omega. So this particular here is this. So it's a cross product of angular velocity and linear velocity in body frame. Okay? And sum of external forces. So that's simple. Later on you will see that computing Fx, Fy, Fz, it will be painful. Like it will be sum of all the aerodynamic forces. Because of the control surfaces or drag, or we will take everything into account later on to compute F. For now, just these are plain inputs to your system. So what is this? How do we? So acceleration in body frame is equal to acceleration because of the rotation and external forces. Okay, we got that down. So now moving on to angular acceleration. So these were linear accelerations. So angular accelerations also, we have the time derivative of angular momentum vector h is equal to the external moments, all the moments applied. So external moments are like the linear, like you have linear acceleration, so you have torques, so forces and torques, right? So when you apply a torque around a particular axis, you will get movement. Okay. So similar approach, we are again differentiating a vector here, and in this case, it will be written same. You have a linear part and a part because of the rotation equal to sum of all the acceleration moments. So later on, you will see that when the propeller is rotating, it gives a counter moment. So your aircraft kind of turns towards that, and we will have to take that into account as well. But because of this and moments because of, let's say you have ailerons, right? So when you do ailerons, here there is a moment generated for a roll. Aileron, different side, moment generated. And when you give a elevator on the tail, there is a moment generated like this. So you have control surfaces which are generating movements, and we are using what? We are using aerodynamics, right? We know that if I do a aileron up this side down here, there will be different aerodynamic forces which will create a movement. So we will incorporate that for here. For right now, we are just saying, okay, let's apply a torque along x-axis, let's apply a torque along y-axis, let's apply a torque along z-axis. Okay? So this equation here, then finally in body frame can be written like this, because let's say all the external forces somehow we are able to compute in body frame. Even if they were not, if they won't be in body frame, we can translate everything to body frame there. Okay, and h of b, the angular momentum is written as moment of inertia matrix multiplied by the angular velocity vector. And moment of inertia matrix is computed this way. Basically, it's basically integration of mass along a particular plane, like in this x, y, and z, in this x and z, x square and y square. So it will give you the moment of inertia along x-axis, y-axis, z-axis, and these are the cross. The off-diagonal elements are called products of inertia. So these are j. And don't worry, we'll give you this matrix so you won't have to compute the top one, because these matrices are computed using some wind tunnel tests, or if you exactly know the mass distribution of the vehicle. And also what I'm doing is I'm just providing you this matrix here, that you know the J matrix given by you, the supplier or manufacturer of the aircraft. Okay. So J is determined using CAD programs, experimentally using, and I think if you people are interested, I can put a paper or a note which basically computes these. I'm not particularly, I'm not interested. I think if you are mechanical engineering folks, this will be of much of interest. Okay, so now putting things back, so this equation can be written like this. We have J multiplied by time derivative of angular velocity and a cross product of angular velocity with H, which is this matrix. Again, we are interested in finding this because that's our P dot, Q dot, R dot, right? The last three equations of motion are P dot, Q dot, R dot, the angular accelerations in body frame. Okay? So to do that, I think we need to J inverse, and see, J matrix is invertible matrix. You can verify that. Moment of inertia matrix is, in fact, I think it is a positive definite and all the nice properties are there. So this is the final equation. So when you are writing equations of motion, you can write in this matrix form as well. I generally use the matrix form, or you can add more details like just individual components, and is sufficient. It will give you a vector P dot, Q dot, and R dot. The later operation is just the equations will, when you invert this, right, J matrix inverse is given this way. So determinant and then cofactors. So determinant, we are calling it as gamma. This gamma here is the determinant of the matrix, this matrix. And MATLAB does this all for you, right? You can just say J inverse, find it. But I'm writing this equation because later on when people design controllers, right, they will need each individual equation. What is the equation for P dot? What is the equation for Q dot? So in that case, you need an exact expression for P dot, Q dot, and R dot. So in that way, it's better to have that expression so that I can individually control each element. But for the S function, you can just write this equation, that what will be the individual term if you solve this. So this will look like this, P dot. So this is nothing but J inverse. And finally, you can simplify in this form. And the external moments are these, L, M, N are the external moments. Make sure you don't confuse this M with the mass of the aircraft, because So I would suggest if you are using M for mass, you can use this double M in your, so these are the external moments that you apply along body axis. So don't confuse this with the mass of the aircraft. Okay. So you see now if I have to change P dot, Q dot, R dot, the external moments come here, L and L, M. So I can change. This also is important. For example, let's say I want to change the roll of the vehicle, right? I can, if you see the roll here, P dot is a function of both L and N, right? So L, M, N. So even if you yaw a little bit, there will be some roll moment because of this. And this gamma 3, gamma 1, gamma 2, gamma 6, they are all parameters depend on which is a function of this J matrix. Okay, when you invert that matrix, you will have them. So now this is the summary of all the 12 equations of motion. In fact, this is the chart you need for putting the S function, right? Because it has all the 12 equations of motion. So first, this, so rotation matrix multiplied by UVW, U dot, V dot, W dot is cross product of the linear velocity and angular velocity and the external forces. Phi dot, theta dot, psi dot is dependent on PQR multiplied by this matrix. And then the angular accelerations are a function of the inertial matrix, and all these parameters are computed for your E. So you can first, and see they are all function of the moment of inertia matrix, right? So JXS, JY, JZ. So you can pre-compute them and then you can compute this equation here. So this is what you have to put in your S function, all these 12 equations of motion. And now what will be the input? Input will be LMN on this side and Fx, Fy, Fz on this equation. And you will verify that if I give f of x, what happens to your aircraft? If I give a moment, what happens to you? So you should be able to see the coupling. Okay? So if you are giving it roll moment, there should be some kind of yaw also with it. So you want to verify that coupling to see all your things are okay. So if this homework is screwed up, if something is wrong and you don't know what is wrong next time when you are putting forces, it will be a disaster. So make sure. So what I will do is I will put, maybe I can show that video to you how it looks like. And yeah, that's it. Equations of motion. So next class will be all aerodynamics stuff. How do we compute f of x, f of y, f of z, and moments, LMN. Moments because of control surfaces, moments because of the propeller, and forces because of aerodynamics, drag, lift, and when you do surfaces up and down, you will get rolling moments, yawing moments, pitching moments. Okay, so this is, and I know it looks bad, but it is not as bad. It's all just writing equations peacefully. Okay. One minus, because see how hard it is to debug this stuff. If you screw up a minus sign here and there, even if a TA will sit with you, it will be hard to debug it. Why is my aircraft doing this? So some of you will be asking this question to me. Okay, I did everything right, and my aircraft is behaving like this. So make sure line by line, recheck it. I think I will also post if there is any errata or any errors in the equation so that you can verify. But make sure that you recheck it before you. Okay. Yeah. Otherwise, yeah. Of course, we will debug it. We will sit down. We will compare our codes and all that jazz. But some things should be easily fixed by us. Okay. So let me show you the video, the output of this file.